Hello and welcome to the LedaFlow Slug Capturing webinar. Thank you for accepting the invitation to join. My name's Mike Branchflower. I'm the Global Sales Manager for LedaFlow within Kongsberg. If you find you're having difficulties with the audio, please go to the audio pane and click on the sound check in blue. This will help you through the process. You can also join over the telephone if you can't get computer audio to work. You'll have the opportunity to submit questions by typing them into the questions pane of the control panel. So that's located near the bottom on the right-hand side of the screen. You should see that. Send the questions in at any time, please, during the presentation and demonstration, and we'll answer as many as we can afterwards, time permitting. Please also note there's a product sheet and a technical note on slug capturing that you can download in the handouts pane. I'm now going to hand over to Wouter Dijkhuizen, who is the LedaFlow product champion. He'll present and demonstrate slug capturing in LedaFlow.
Thank you, Mike, for the introduction. So this webinar is about slug capturing. I will quickly explain a little bit about the slug capturing technology and LedaFlow before we start, and then most of the time in this webinar will be spent on a live demonstration afterwards. So slug capturing, it is a technology where waves and slugs are automatically resolved by using a very small cell size, typically about 5 pipe diameters. So let's assume that you have a let's do it in feet. If you have a 1 foot pipeline, then it's about 5 foot cell size. So that's quite small by flow assurance standards. We're using a higher order numerical method, which gives less numerical diffusion, and that means that we don't need to use as many cells as otherwise would have been required. And then the physical models in LedaFlow are restricted to the stratified model in near horizontal sections and the annular model in vertical sections. So for near horizontal inclinations, that means that gas, oil, and water each have their own individual velocity, and you can have slip between all 3 of the phases. So that is important. And also the interface friction model in LedaFlow has been modified for high liquid fractions. So that is particularly for waves and slugs. So that has a slightly different treatment from the standard model. And that is to give the correct slug propagation. And then finally, we have gas entrainment at slug fronts. That means that gas bubbles can get entrained at the front of the slug, and they move through the slug and maybe come out the other end again. And that is very important in order to get the right momentum conservation and the proper slug velocities. Okay, then it's quite important to stress that so we do not track slugs as discrete elements. So we don't number the slugs and move them around the pipe like you would with, for example, pigs. But the slugs, they are actually resolved on the Eulerium mesh as being holdup. So essentially, all LedaFlow knows is what the liquid holdup is in every cell. And based on that, we do the slug capturing. So as a consequence of that, we can handle any kind of wave instability. So slug capturing, even though it has slug in the name, it doesn't just handle hydrodynamic slug flow. Also small waves or longer waves, surge waves, hydrodynamic slug flow, of course, but also terrain slugging. All of those different wave instabilities, that they can be handled by slug capturing. So it's completely unified. And then also because of this capturing technology, one of the consequences is that slug statistics, they're not automatically calculated because we don't know exactly where the slugs are. So they have to be post-processed after the simulation. And I will show that in the demonstration later on, how exactly this works. A few more notes about slug capturing. So there are no specific input parameters or tuning factors available in this model. So essentially, you're using the same kind of model as you would for any kind of flow assurance task. which is very convenient. The only difference is that you need to turn on the slug capturing module, so that replaces the standard physical models. And then you need to remesh in order to have an accurate, sufficient resolution. But that is all. There are no other settings to worry about. So it's very user-friendly. And also, sometimes we get some questions about why slug capturing is currently in beta status. And that is because of two reasons. First of all, the grid dependency. So this is not specific to slug capturing, but it's just because of the small cell sizes that we use. So typically, if you have very small cell sizes, maybe 1 pipe diameter in length or smaller, there can be some unphysical wave growth. And that is related to the ill-posedness, as it's called in literature. So those are basically numerical artifacts that you get because of the way we treat the pressure in the Navier-Stokes equation. So that is something to be aware of, but it should be noted that typically you don't need these very small cell sizes to do your calculations anyway, so there's not that big a problem. But ideally, we would like to prove what kind of grid size is the results get grid independent. And for that, this is an issue, so it's something that we're actively working on. And also the calculation speed, because of the small cell size, it can be an issue, particularly for long pipelines that have a small diameter. So interestingly enough, for slug capturing, it's actually an advantage in terms of calculation speed in order to have a large diameter pipeline, because it's less restrictive on the cell size. Okay, then we go to the live demonstration. Okay, this is the base case that I've prepared for this demo. So it consists of a 1 kilometer pipeline. The pipeline, we're not using an energy equation, but so we're just using a constant temperature because it's not really important for this demo. And then the diameter of the pipe, just convert this into inches, so it's almost 8-inch diameter. And then the wall roughness is 45 micrometers, which is the default wall roughness that we have in LedaFlow. It's a very common value used for flow assurance. Then at the flow boundary at the inlet, so we're inputting 40 kilograms per second, and then we have 1% gas and 99% liquid by mass. So there's quite a lot of liquid flowing in and a little bit of gas. And then I've chosen this case because it gives hydrodynamic slug flow. I can also mention that this pipe is perfectly horizontal, which is relatively difficult for hydrodynamic slug flow calculations. So it's a good test case for slug capturing. We can just quickly run this case. So I'll just initialize it using the steady state preprocessor and then run it for 10 minutes. And the simulation is done already. So then we can have a look at results. So this is first of all the liquid volume fraction in the pipe. We can see that it's almost constant because this y-axis is very compressed. So it's about 76% liquid by volume. And then the physical flow regime identifier, it is 3, which means that this is hydrodynamic slug flow. So we already know that. So that's the basis for this case. And if we if we just play this as a movie, we can see that there are no dynamics in this case. It's completely steady state because we're using the unit cell model for hydrodynamic slug flow. So the actual dynamics that you get in hydrodynamic slug flow, they're not showing because this unit cell model it simulates hydrodynamic slug flow in a time and spatial averaged way. Okay, so this case we're going to use for slug capturing now. So in order to do that, I will first duplicate the case. So we can just give it a different name. So we'll first run slug capturing with a relatively coarse mesh. that will be 20 pipe diameters in length. So now I've duplicated the case. The first thing we need to do is turn on the slug capturing in the case settings options. So we'll just put this to yes, and then we press OK. You can see that slug capturing was enabled, and also the higher order discretization was automatically turned on. Then the second thing we need to do is remesh the pipeline. So then we can use the delta x over d method in the mesh editor. So this is especially for slug capturing. And then we're using a 20 pipe diameter mesh. So if we run this, we can see that cell length has become about 4 meters, as expected. So now the simulation is set up properly, and we can run it again. So we will initialize and run for 10 minutes. This goes quite quickly, so we can just wait until it's finished. Now it's done. So since we've duplicated the base case, all of the plots that I created for that one, they're also present in this case now. So I can just reopen the existing plots. So then we get the plot for the volume fraction and physical flow regime again. So we can see that liquid volume, first of all, is a little bit higher than in the case with the standard model. So it's about 81% liquid. And there's a very small instability here. But if we just play this, we can see that this instability that we were seeing, it's actually it's nearly disappearing. So actually there are not really any dynamics in this case. This is only there probably because of the startup effects. So it might disappear when I run this case for longer. Then the physical flow regime, it is stuck to 1, which means that it's stratified flow. And that is because the underlying model for slug capturing is considering stratified flow. So if you use slug capturing, this physical flow regime identifier, it will basically no longer work. So it's actually better not to look at that one. So we'll just remove the plot for now. So in the end, the results show that we've now used slug capturing with a 20 pipe diameter mesh. And then there are no real dynamics in this case, and certainly it doesn't show hydrodynamic slug flow. So the next step is to refine the mesh in order to see if we can replicate the hydrodynamic slug flow then. So we'll duplicate this case once more. So we'll just call it something else. We'll try it with the 5 pipe diameter mesh, which is the normal recommendation. And I will do a small trick here, which is to duplicate the last time point of the previous simulation and then reset the time to 0. So we can use this result as a starting point for the next simulation. Then I will remesh the case. So we'll use 5 pipe diameters. So now the mesh size has become about 1 meter. So that is all I need to do, and then I can run this case again. So we'll not initialize the case now. Why? Because we are using the result from the previous simulation as a starting point. And then the reason why this is a good idea is because it has already reached a steady state liquid holdup. So if I were to initialize again now, we're starting from the steady state preprocessor holdup, which is using the standard model to compute the liquid holdup. So it's a little bit off from slug capturing. And then the consequence of doing that would be that the simulation has to run for longer. So by now taking the simulation result from the coarse mesh slug capturing case that we ran before, and then running it, I don't have to run the simulation for as long, and I'm saving quite a lot of simulation time. So I'll just run it now. You can see it's going now. So in LedaFlow, while the slug capturing simulation is running, or any other simulation, we don't need to wait with analyzing it until it's done. So I can already open the plot and we can see what it's up to. And then if I press the auto refresh button over here, then we can see that slugs are being formed now at 2 locations in the pipeline. So if we wait a bit longer, we can see that everything over here is now showing hydrodynamic slug flow. And then the slug flow, it seems to sort of start at about 20% of the length of the pipeline. So around 200 meters length, that is where the slug flow definitively starts. And then there's a little bit of variation in the shape and size of the slugs, but it looks relatively regular, as you would expect for hydrodynamic slug flow in a case like this. Okay, so that looks good. So we can actually replicate the hydrodynamic slug flow here. We can also have a look at it in the 3D viewer. Yeah, if you zoom in a bit, you can see, you can clearly see here that you get this characteristic Taylor bubble shape. So that looks good. So we know it's we're actually simulating hydrodynamic slug flow. I can also play this a bit, so you can see that the slugs are being formed here, and then they are propagating through the pipe. Yes, so let's see, the simulation is almost done. So we can have a look at some of the post-processing capabilities to finish off this demonstration. So we're using the slug statistics module now. So we also have a slug size module, but that is more for analyzing things like large waves or maybe terrain slugging. So you can compute the size of your separator or slug catcher. But the slug statistics module, it provides you with the statistics of hydrodynamic slugs typically. So this is the input that the model has. So it's using both a trend logger, which is currently using the pressure node at the outlet. So by default, LedaFlow logs the volume fraction there, which we will use to find the start and end time of each slug. And then at the same time, we're using a profile logger from the corresponding pipe, which is this one. And this profile logger, it is also giving the volume fraction, but this is the volume fraction along the pipe. So we can use this profile logger to find the length of the slugs. And then this trend logger, it already gave the duration of the slugs. And then combining the two gives us the velocity of the slugs passing by. So the main input here is the volume fraction threshold. So that is this light blue line over here. And that one is used to identify when the slugs start and end. So I can increase this value a little bit to 90%. And then we can see here that this nicely captures when the slugs start and end. It's maybe a bit clearer if I zoom in. You can see this is the slug, and then the start and end point are captured adequately if I put it at 90%. So that one is okay. Then I need to select a start and end time for the analysis. So you can see here that at the start of the simulation, there's some small stuff going on. So the slug flow is not entirely stable here yet. And then it seems like we have some stable slug flow over here, but there's some disruption over here. So this is where if you paid close attention earlier, you saw that initially in this simulation, we got slug flow in two different locations in the pipeline. And then over here, this is where where these slugs are pushed out. So this is also sort of a transition to stable slug flow. So we want to analyze, I would say, from 300 seconds to the end of the simulation. That will give us some better results. So just put it like that. So everything between these two yellow lines, that will be analyzed now. So this looks reasonable. We can just run it now. Now the analysis is done. Then we can look at the statistics. So I always look at this statistics plot first to see if the results are reasonable. So we can see the slug length over here. It's a little bit of a normal distribution, but this looks good. So on average, the slug length is somewhere around, let's say 3.5 meters. And then the velocity, it has a very narrow distribution, like you would expect for hydrodynamic slug flow. So this is about 3.6 meters per second. And then the duration of the slugs, it's also a little bit wider distribution because obviously we have a distribution in the slug length, which is sort of equivalent with the duration. So this is the statistics plot, so you can look at the results, but there's also a data table with the raw data for each and every slug that it has identified. So you can use this in your own post-processing if you want to do something more with this. And there's also a summary table which gives you the averages and the min and max values here. So you can see here it found 61 slugs and with these properties. Okay, that concludes the demonstration. I guess we'll go to the questions now.
Okay, thank you very much for that, Wouter. Yes, we'll begin to answer some of the questions submitted. We've got a few questions from Phil Manfield at Shell that we need to address on slug capturing. I'll read you out the first one. What are the additional mechanistic model features enabled when you switch on slug capturing, Wouter?
Additional features. So yeah, it's I wouldn't really call them features, but it's just the fact that we're using a separated flow model, and then on top of that we have gas entrainment at the slug front. So that's basically it. And then the friction around slugs is treated slightly differently as well. So it's not really a feature, but it's using a different multi-phase model basically.
Okay, and then there's a question around closure relationships around slugging behavior as well. Slug translation.
I just described that. That's what I just described.
Yeah, so it's related to that, isn't it? That's right. And then the relationship between slug velocity and slug length.
Yeah, so basically the slug velocity, as you saw in the post-processing earlier, that one is very uniform. But and that is to be expected for hydrodynamic slug flow, because this is just a simple straight pipe. But basically the slug length, it's not really related to that. So the slug length, it can be much shorter and still have the same velocity or longer.
Yeah, and the final question, which I think you've really already answered anyway, around how the slug capturing actually works, is about hold-up profile and the slug tail model to get the tailor bubble shape. But I mean, this is just falling out.
So we don't have any special models to get the right bubble shape. It's only a consequence of the friction models, basically.
Yeah. Okay, any more questions from anyone? You've still got a few minutes to type in some questions before we close the webinar, so please feel free to do that.
While we wait, we can enjoy the 3D visualization a bit more.
Yeah. Doesn't look like anyone else is going to submit any questions, so I think what we'll do is some people saying thank you. So here we go. How about terrain slugging then, Wouter? What would you say about investigating terrain slugging with LedaFlow in general and slug capturing?
Yeah, so that's a good point. So slug capturing, is totally able to handle terrain slugging as well. But if it's pure terrain slugging, that by that I mean if you don't have any interaction with hydrodynamic slug flow, then the standard model is perfectly capable of dealing with that as well. So you don't really need to do slug capturing for that. But so the only benefit from slug capturing is if you have interaction between different kinds of slugging. That's where you need to use the slug capturing method. But otherwise, the standard model is capable of handling it just fine.
Yeah, so there's another question around terrain slugging about, do we have examples? I mean, we have plenty of examples in LedaFlow of terrain slugging running the standard model. There are also examples of hydrodynamic and terrain slugging interacting as well.
I can just quickly show that. So we have these sample cases that they were updated in version 2.3 of LedaFlow. So we have, for instance, this flow line with a riser that is slugging. So we do different things with that, like making turndown curves, but also separator sizing. So there's, if you, for instance, open this this sample case, you can see here in the notes page, there are some instructions on what to look for. So that's quite interesting if you have this available. And then we also have many other sample cases that look at different things, like for slug capturing. So this wave growth case is quite similar to what I've just shown. So it's also a good case, and you can look at different things as well.
Yeah. A couple more questions popping up because we have a few minutes left. Pressure fluctuations. I mean, we could have plotted pressure fluctuations if we chose to do so.
Yeah, I can just show that right now.
Yeah.
So LedaFlow comes with a whole lot of outputs by default. So I didn't select anything special for this case. So this is out of the box. So you can see here that yeah, this is just basically the case starting up and then initiating the slugging. And then yeah, at the end you can see that there's these small oscillations that are caused by the hydrodynamic slug flow. But the amplitude is very small. We can also plot it along the pipe, and then you can see why. Yeah, so here you can see that there's these very small bumps in the pressure, and that is the pressure effect from the hydrodynamic slugs. But because there are so many hydrodynamic slugs in this pipe, basically all of them combined, they don't produce a very big oscillation as at the start of the pipe, because there's just so many of them. So that's the reason why it's not so interesting to look at pressure fluctuations for hydrodynamic slug flow, because it kind of balances out because of the sheer number of them.
Yeah, a few more questions popping up right at the last minute. Francis at Total asking about long simulation times with 5 ID or 5 diameter mesh cases, but I would encourage you to try this technique of using the 20D and restarting and then running 5D. The overall simulation time comes down drastically. At least that's what we found on some simulations. So I think that's the answer to that one. Did we achieve mesh size independence with 5D cell size? Not really better, but do you want to just mention something on that?
Yeah, for this particular case, I didn't try that. So, but we might. But yeah, as I showed in the presentation, this ill-positiveness makes it a bit tricky to prove the mesh independence, because we know that there will be some unphysical waves appearing if you go to a smaller cell size anyway. So it basically prevents us from proving that the results are mesh independent. So that's the main problem behind it.
Okay,
so
another
we would
question.
like to show that, but it's just not possible at the moment.
Yeah, yeah. Another question from Atsushi from IO Oil and Gas about tuning for slug capturing. Is there any tuning that we can do around time intervals, segment lengths, intervals, etc.?
No. So there's no tuning in slug capturing basically. So this is designed as a predictive model. So it will just yeah. So the only thing you can adjust is the grid size, but besides that, there are no tuning functions. So yeah, the results are the way they are because of the physics.
Yeah, and there's another question very similar to that I won't read out in the interests of time, but yeah, essentially there's not a lot of tuning parameters here. There's tuning parameters within LedaFlow itself, but you would just still run slug capturing, and that's really it. With a larger mesh size, no, you would get different results with a larger mesh size and then going to a smaller mesh. The larger mesh size was really just to initialize the simulation to then rerun on a fine mesh. You could, or you probably will get different answers, not always, I guess, but I would think you would. Presentations that we can watch offline, please. That's Rogi has been asking me about that. So yes, what we're doing is we're loading up webinars and tutorials and things like that onto the Kongsberg YouTube channel. You will also get sent a link to this presentation as well. So if you go onto Kongsberg YouTube and start looking for LedaFlow, you'll find videos of that. You'll also find videos of integrated simulation with dynamic process simulators as well. What PBT files can we use within slug capturing? I'm not aware of any issues there, Wouter, but can you just confirm?
Yeah, you can use any kind of PVT. So that includes multi-flash for compositional or PVT tables, black oil, or even the constant PVT.
Yeah, very good. Okay, well, yeah, thank you. We're out of time, so thanks again, Wouter, and thanks to everyone who attended. As I just mentioned, you should get a follow-up email within a day with a link to a recording of the webinar, so you can view the video again if you missed anything. And of course, if you have any other questions on slug capturing or LedaFlow in general, please just send me an email and I'll get back to you as soon as I can. On behalf of Kongsberg, thanks for joining the webinar, and we hope to see you at the next one. Enjoy the rest of your day. Goodbye.